Okay, so let me try to finish a little bit of what is left in module 2 chapter 1, which is PCA, followed by some basic stuff on the split of data into training, testing, etc., and little bit about software that is being used to conduct machine learning. So these are the three things that we will do today, and I'll try to cover this in a short video so that we are done with module 2 chapter 1. Let's start with PCA. Very important concept, and if we want to understand this statistically in depth, it is quite a, especially for people who don't have a math background, they might find it difficult to understand. I will try to keep it crisp. At the same time, if you don't understand this, there is a lot of content available, either in forms of textbooks or more in-depth videos. You can go through it, or you can also skip this because at most there will be one question from PCA. So what does PCA stand for? Is that it's a kind of unsupervised learning. And the primary purpose of doing PCA is dimensionality reduction. So what do I mean by this dimensionality reduction? See, each data point we have been studying, it comprises of tons of features. And sometimes these features, and just to reiterate, if this is a customer, the customer can have a variety of features which can describe that customer's financial attributes, demographic attributes, some other attributes. Okay, so sometimes the features become so many and so big that it becomes difficult to comprehend, and also it becomes difficult to mathematically understand them or find some patterns or even visualize them. So in such cases, we try to find out a smaller subset of, I'll say, features. K is much less than n, which can describe the maximum variance in the data. So what I mean by variance in data is that since these data points, these are distinct data points, so they have to be different, and there would be a lot of variance in the data, but we may not need all the n features to describe that the variance between the data points. Sometimes there can be features, let's suppose feature 1 and feature 6, I'm just making this hypothetical, they might be highly correlated with each other. Okay, let's suppose their correlation is 0.95, that is their correlation. So which means that it may not be very important to keep both these features. So principal component analysis helps you to find out principal components that, and it is a sequential process where principal component when is going to give you the maximum variance of data, and it is nothing but a linear combination of your input features. So what do I mean by saying linear combination? This means that principal component is nothing but, let's suppose there is a weight bi of f1, it can be bi2 of, say, feature 2, bi3 of feature 3, and it may skip also, some of these bi's can be 0, etc. So that's going to be your principal component 1. Then your principal component 2 is going to be orthogonal to principal component 1, and it is also going to be a linear combination of features like principal component 1, but it is going to be the next biggest contribution to explain variability. You will see a graph in many books, even GARP will have this graph where, let's suppose this is the variance explanation, and let's suppose these are your principal component 1, principal component 2, principal component 3, 4, let's suppose 5, and let's suppose this is 100%. So first principal component itself gives you say 60% of your variability, and your second is going to give you probably say 10%, and then it is going to become 0 and 0 itself if there is 6. So in a very reduced number of principal components, you will be able to explain a large proportion of your variability. Now just for your just for your reference and inquisitiveness, I also think it can be a good idea to explain this you what this interprets to mathematically. So let's suppose you have n features. So how do you find this principal component? Let me try to since I have a very strong statistics background, so I personally feel that this is important for your interpretation, but in case you do not understand this, you can skip this portion as well. So the first step that we do is we try to find out the pairwise correlation of all of these features. So let's suppose F1 and F2, F2 and F3, F1 and F3. So between Fi and Fj, we try to find out the correlation. So now what correlation means is that, correlation between say x1 and x2 is nothing but, xi minus xi bar sigma 1 to, since we are talking only about pairwise correlation, it is 2 only, but it can be 1 to k and then divided by the population, and sometimes it is, if it is a sample, it is n-1, if it's a population, it is n. So consider this as n-1. So that gives you the correlation between two variables, and when you do this for all your n variables, you can create a matrix. So that matrix is going to be n cross n matrix. So it's going to be a matrix where your lower triangle and upper triangle could be the same, because the correlation between say 1 and 2 and 2 and 1 would be same itself. So you'll get a correlation matrix n by n. Let's call that matrix as A. So so the equation to get the principal component goes like this. It says that A, if it is multiplied by another matrix X, should be a scalar value lambda multiplied by the same X. Okay, so this is how your principal components are computed. Lambda is called the eigen value and your X is called the eigenvector. So eigenvalue is nothing but your variance of those principal components in the order, and eigenvector is nothing but the linear combination of features. Okay, so lambda is going to be, let's suppose lambda is your 10 and 5 and 2 and so on, based on the number of features that you would have. Let's suppose it is only let's suppose this is 3 and 2. Okay, so this is your lambda. That means that this 10 means this is 10 out of, if you sum everything together, it is 10 out of 20. So 50% of variance is explained by your first principal component. The 5 out of 20, which is 25%, is explained by this, and so on and so forth. So that's what lambda is going to give you. X is going to be a linear combination of the features. So that's going to give you the linear combination from this X vector. Now, how do you actually solve this? You can say A into X, it's like your algebraic equation, A into lambda into X equal to 0. And then you can say, X you can take as common, then it is A, and lambda, since we are talking about vectors, it's going to be lambda into I, it is going to be 0, which means that A should be lambda into I. I is called an identity matrix, you may be knowing. So when it is multiplied by any matrix, it gives the same value as the term that it is multiplying this with. Okay, so this is how you can derive lambda, and once you derive lambda, you can use this equation to derive x. So this is how principal component is derived. You don't have to derive principal component in the exams, but I thought it is good idea to let you know. So that's about the principal component analysis. The second thing that is left in this chapter is about how do you split the data. So let's suppose you have a data set and you need to, as a part of your exploratory data analysis, you need to split the data into 3 parts. One data is called for training. The second part is called the validation. And the third portion is called the testing. Now, while you are going to train the models, and we are going to talk about models at a later point of time, but just understand that model is some kind of a mathematical format which is going to estimate the value that you are trying to predict, whether it is classification, regression, etc., etc. So if we use the entire data for training, generally it is going to overfit your data. So what I mean by saying overfit is that it is not going to generalize this properly. It is going to overfit this to an extent that if you run this on some data which is not seen, it may not be the right thing. Let's suppose this is your data. Let's suppose this is height and this is weight. So if you put everything together and you try to generalize this so much and so forth, the line is going to come like this. So tomorrow if there is somebody and we are saying, okay, his height is like this, what is going to be the weight? So it is going to say the weight is this much while it is this much. So instead of creating a kind of a generalized line like this, it is going to create a more complex line, and that's called the overfitting of data. So the purpose of doing this split is that we hide out some portion of the data from the training itself, so that we can do the verification and validation and testing at a later point of time. So that's the entire purpose of keeping a separate portion for training, a separate portion for validation and testing. So training is going to build your model, build your say draft models. So let's suppose you build 2 models, M1 and M2, on this training data. Now you need to validate these 2 models, which of these models is better for you. So that kind of a competition or that kind of a validation is done on the validation data set. And let's suppose here on this validation data set, which you have kept aside, you find M1 to be doing better than M2. So you select M1 from this step. And then in the testing phase, you keep another portion of data where you try to test M1. And how do you test, what metrics, what KPIs, that's kind of a separate topic. There is a separate chapter on it. But then let's suppose you find out that M1 is giving you 90% accuracy or 90% efficiency, and that's how you use your testing data. Now, how do you generally divide your data set into these 3 portions? Most of the times you keep 2/3 of your data for training itself. That's what Garp also mentions, and that's how it is generally being done in real life scenarios also. The remaining 1/3 is split between validation and testing. So you can think that 1/6 of data is here, 1/6 of data is here. There are times when you don't need validation and you can directly train and test the models. So this should cover your splitting of data into training and testing. But sometimes if your data is not too large and you don't want to say you don't want to give away some of your, let's suppose there are only 100 data points. So if you use only 66 out of 100 for your training, it might not be sufficient. You might want to use all 100 data points. So in that case, there is something called as k-fold distribution, where you, let's suppose k is 10 in this case, so you make 10 buckets of 10 each, and then you say hide out one or two of them, and then you train on the rest of the buckets, and you keep trying various permutations and combinations of this till the time you stabilize your model. And this is called the k-fold split of data. There can be a scenario when you have, let's suppose you have a time series data. So time series data or any data that is, we had discussed that data can be longitudinal or cross-sectional. So if it is a data where the sequence of information is important, in that case, generally, and let's suppose this is the sequence of data, you keep the fresh portion of the data for testing, the next to fresh is for validation, and this historical data is for training. So this is how you split your data if it is a longitudinal data, or if it is a small data and you need to do some kind of a cross validation. The last reading, module 2 chapter 1, is about software. Very, very basic reading. It's about what kind of software do you use for machine learning, because these days nobody is going to do all these calculations, whether it is eigenvalues or eigenvectors, or at a later point of time we can also, when we read about deep learning networks, there are more intense mathematical calculations. So all of this is done by software. Generally, there are I would say 3 to 4 types of softwares that you can use. One is your open source software, then you have cloud, then you have, say, you can say it as a closed system software or proprietary software. Some of the cloud is also proprietary, but a programming language which is more proprietary and closed source. And the last but not the least, there can be some tools for people who don't like to code, low code, no code kind of tools. Okay, low code, no code kind of tools. So in open source, the most important languages that are used are R and Python. Python being more popular recently than R. R is preferred by statisticians and Python is preferred by programmers. And then Python will have a lot of packages. Since it is open source, anybody can create a package and put it on the Python repository. But there can be a lot of packages like pandas, numpy, or TensorFlow, or your PyTorch. So there are a lot of packages within Python that can help you to do machine learning in a much easier manner. You don't have to actually get into the math of algorithms. You can just call them like an API. R is also equally good, not that used these days, and this can also have packages like Caret, etc., which can help you to do some kind of visualizations, etc., etc. You can also do ML on the cloud, AWS, Azure, and GCP being the biggest ones, and then there can be some less popular ones, and each of these will have their own ecosystems to help you with machine learning. AWS will have Bedrock, Azure will have ML Studio, GCP may have a studio of their own. On the closed or more proprietary stuff, is the most popular is SAS. SAS used to be the most popular language for machine learning. We used to use a lot of SAS 15 years back, while there was very less or negligible Python. But and the new version of SAS, where it is on cloud, is also there now. It's called SAS Via, but not that popular these days. On the low code, no code side, there can be tools like, say, Nime. So pronounced with a K, but K is silent. Nime, Then there is data IKU and data robot. There are too many of them, you name it and it is there. So all these tools are going to give you some kind of a drag and drop kind of a features and out of the box models, and all of these tools can give you, and these tools will help you right from your EDA or data collection till your say model design, model training, testing, etc., deployment, and also with the model management. Okay, so that's all about that. Brings us to the end of module 1 chapter 1, and we'll start with the chapter 2 in a new video. So thank you very much.